Good morning, everyone. Let's start. In the previous class, we saw a number of information theoretic quantities. The entropy, h of x, for a given PMF px, the entropy corresponding to the random variable x is defined as follows. Given two correlated random variables, x and y, with joint distribution pxy, we define the conditional entropy h of x given y as the summation over all xy p of xy log 1 over p of x given y. So this is to be interpreted as the amount of randomness in x given that you have observed y, whereas h of x is the amount of randomness in x given that you have made no observation at all. Right? So, and similarly, the mutual information between x and y, that is the amount of information that x gives about y or y gives about x, is defined as follows, and it turns out to be equal to the difference in the amount of randomness that was originally there in x minus the amount of randomness that is left in x given that you have observed y. Right? So it is h of x minus h of x given y, and is also equal to h of y minus h of y given x. All right, and we also noticed that if x and y are independent, then pxy is equal to p of x times p of y, and therefore the mutual information is equal to 0. Right? What this means is that if x and y are independent, then h of x given y is equal to h of x, and h of y given x is equal to h of y. So the amount of randomness that is left in y after having observed x does not change. It is equal to h of y, and that is to be expected. Right? So p of x given y is equal to p of x. So similarly, the KL divergence or the relative entropy between two distributions P and Q over the same alphabet is defined as summation over all x, P of x log P of x by Q of x. And we also noticed that the mutual information between x and y can be written as the KL divergence between the joint distribution and the product of the marginals. Okay. So one point to note is that this function, so the mutual information is symmetric in x and y, right? But the KL divergence is not symmetric in P and Q. So dpq in general is not going to be equal to dqp, right? Because dqp would be summation q of x log q of x by p of x, which is in general going to be different from this particular quantity. Okay. So are there any questions before we proceed?
Sir, sir, actually, what is uh, the significance of the scale divergence?
So as I
That
mentioned, the KL divergence is sort of a measure of distance between two distributions. It is not exactly a distance. It does not satisfy all the properties that a distance metric has to satisfy. But as we shall see, if two distributions are sort of far apart, then the KL divergence is large. Whereas if they're equal, then the KL divergence is equal to 0. Okay, it's a non-negative. We'll see that it is a non-negative quantity, and it sort of increases as the distance between, in some sense, as long as the two distributions are very different from each other. Okay, and the KL divergence arises as an operational quantity in many applications. So, for example, when you want to test between two distributions. So, for example, if you want to design a classification algorithm uh, for distinguishing between samples between two distributions. So maybe you observe a sample which, or you observe n samples which are either distributed according to P or distributed according to Q. You don't know which. Then the minimum probability of error that you can achieve turns out to be roughly 2 to the minus n times dpq. Okay, so that's one place where it arises. It also arises in the context of data compression. So if you try to compress uh, according to, so assume that you have a sequence which is distributed according to p, but you don't know what the actual distribution is. So maybe you estimate the distribution to be q, and you design a compressor for q, for the distribution q. Then the minimum the minimum expected length turns out to be equal to h of px. So xn is distributed according to px, but you design a compressor based on qx. Then the minimum expected length that you can achieve turns out to be roughly h of the expected length by n. So the rate turns out to be roughly h of px plus d px qx. Right. So since you estimated the distribution wrongly, there is some penalty to be paid. You cannot achieve the optimal compression rate of h of px, and the penalty turns out to be equal to the KL divergence between the two distributions px and qx. So if your estimate is better, then this penalty is smaller. If the estimate is bad, that is qx is very different from px, then the KL divergence turns out to be large.
But if we design based on px, then we won't get that.
Yeah, so if the true distribution is px, if xn is actually distributed according to px, and you design a compressor and you somehow you would know that it is exactly equal to px, then there is no penalty. The minimum rate is equal to h of px. But then in reality, you can't estimate the distribution exactly, right? There is in general some error in your estimate. And so you estimate it as qx, so there is some penalty which turns out to be px, dpx qx.
And sir, actually last class also you said, but we didn't get some clarity. Like px, qx, we're taking like two different distributions on the same random variable kind of thing. Like, can you
on the same
take
alphabet? It is not the same random variable, right? So,
Okay.
so for example, I mean, it can be anything, right? So you have a random variable x, maybe x1 is distributed. Let me call this x, which is distributed over, which is say Bernoulli p, right? And maybe x prime, which is Bernoulli q. So these are two different distributions. Bernoulli p and Bernoulli q are two probability mass functions over the same alphabet, which is 0, 1. Right? So I can call this distribution px is, sorry, px of x is p if x equal to 1 and 1 minus p if x equal to 0. This is one PMF, whereas this is another PMF over the same alphabet, which is q when x equal to 1 and 1 minus q when x equal to 0. All right. So these correspond to different random variables, but both these random variables have the same support, which is 0, 1. They are distributed over the same alphabet. Does that make sense?
Yeah, okay, sir.
Okay. So now in today's class and the next, we're going to look at some properties of entropy, conditional entropy, mutual information, and KL divergence. And it turns out that most of the results in information theory are essentially based on these properties of mutual information and K divergence. In fact, so we look at two classes of properties. One is non-negativity. We'll see that all of these quantities, h of x given y, ixy, and dpq, these are non-negative for discrete random variables. So as long as these are distributions on some discrete alphabet, all of these quantities are non-negative. And in fact, so we'll also see that these, of course, these are all functions of distributions. So we'll see that some of these are convex in some of the arguments and concave in some other arguments. So we'll investigate the convexity properties of each of these functions. And the non-negativity and convexity properties of these functions are in fact very important and are widely used in information theory and statistics. Okay, so that's the agenda for the rest of this course. Since we don't have enough time, I won't go through all of the proofs in full detail, but then I'll definitely provide material for the parts that I've missed out. But these are very important properties. Okay. Okay, so maybe before we start, we can perhaps have a quick quiz regarding the topics that we've seen previously. So I will assign it on Google Classroom and also share the link over here. All right, so the link has been shared in the chat box. You can maybe take 4 or 5 minutes. Can maybe take 1 more minute. Is everybody done? Anyone yet to submit the responses?
Yes, sir.
Everyone's done? I will stop accepting responses. All right, so there were two questions. One was what happens to the mutual information if X and Y are independent and identically distributed Bernoulli random variables. So as we just saw, if the random variables are independent, then the mutual information is equal to 0. So the correct answer is 0 bits. Another question was if X is a Bernoulli p random variable, then which of the following is always true? We calculated, sort of plotted the entropy of h of x, and for a Bernoulli random variable, it varies between 0 and 1. So the correct answer is that the entropy is always between 0 and 1. Okay.
Sir,
Yes.
in between, I think there was network issue from my side. I couldn't hear the answer you told for first question.
So
Can
the
you just
first
repeat
question
it?
is that if X and Y are independent, then the mutual information is equal to 0. So the correct answer is 0 bits.
Okay, sir. Thank you.
Okay. All right, so let's continue. So we'll now investigate some properties of the entropy and mutual information. All right. So the first property we'll see is the so-called chain rule. Okay, so we know what the entropy and mutual information are for a single random variable, or maybe a pair of random variables. What happens if we have a sequence of random variables? Right. So if I have, let's say, two random variables, h of x, x for x and y, so x comma y are jointly distributed according to some pxy, right? For example, x could be the input and y could be the output of a BSC, or it could be any other problem for that matter, right? So x and y are jointly distributed according to pxy. Then the joint entropy of x and y, h of x comma y, is equal to this particular quantity. So summation over all xy, p of xy log 1 over p of xy. So it's identical to what we had for a single random variable. Now, let's try to split this. Okay, I will write this as summation pxy log of, let me write as px of x, py given x of y given x, right? I can always do this. Now, since this is the log of a product of terms, I can write this as a sum of two logarithms. P of xy times log 1 over P of x plus log 1 over Py given x. Right? Now let me sort of multiply these and look at the two summations separately. So it is summation over all x comma y pxy of x comma y log 1 over p of x plus summation over all x comma y log 1 over py given x of y given x. Right? Can someone tell me what the first term will be equal to? Okay, can someone tell me what the second term is equal to?
Conditional entropy.
Correct, it's the conditional entropy h of y given x. Right, so this is by definition equal to h of y given x. Okay, so now let's look at the first term. I will split this summation into two. So I can write p of xy as p of x times py given x, right? Okay. Now I'm just writing it out separately. So log 1 over p of x, and I'll split the summation. So the summation over all x, summation over all y. Okay, I've done nothing else. So I split p of x comma y as p of x into p of y given x, and I'll take all the terms with only x on one side and those with y given x together. Okay, so now what is this term equal to? What is summation over all y p of y given x for any x?
1.
Marginal of x.
It's equal to 1, right? So summation over all y p of y given x is equal to 1 because it's a conditional probability. Right? It's a conditional PMF. So what remains? So this quantity is equal to 1. So what is that quantity which remains?
H of x.
H of x.
Exactly. So it's h of x. So h of x comma y is equal to h of x plus h of y given x. All right. So this is, since you can sort of interchange the roles of h x and y. So h of x comma y. So this is also equal to h of y comma x, which is equal to h of y plus h of x given 1. So the total uncertainty in x and y put together is equal to the uncertainty in x plus the residual uncertainty in y given x. Right? So that is why it's called a chain rule. If you have two random variables, then the total amount of uncertainty in the two is equal to the amount of uncertainty in one plus the amount of uncertainty in the second one after having observed the first one. So think of it, so one way to interpret it is that, well, you have two quantities of interest. what is the total amount of information you're getting by observing the outcomes of those two random variables? It's something, it is h of x comma y. But this is also equal to the uncertainty if you first observed x and then observed y. So if you first observed x, then the amount of information you get is h of x. But then later when you observe y, what is the amount of information that you get? Well, you already got some information about y previously by observing x, and the amount of information that you get after observing y is now h of y given x. All right. So similarly, if you have, let's say, x1, x2, x3, if you have three random variables, then the joint entropy of x1, x2, x3 is equal to h of x1 plus h of x2 given x1 plus h of x3 given x1 and x2. All right, so the joint entropy of three random variables is equal to the entropy of any one of them plus the entropy of the second one conditioned on the first one plus the amount of plus the entropy of the third one given the first and the second. All right. So for example, if you're trying to compress three different sources, x1n, x2n, and x3n, then it turns out that the total rate of compression, the optimum rate of compression, x1n, x2n, x3n by n, if let's say these are IID sources, then the minimum rate of compression is the same whether you compressed all of these together or you compress the first one and then compress the second one based on the first one and then the third one based on the first two. Right? So this is what it says. So you can compress these jointly or you can compress these sequentially, one after the other. But when you do it sequentially, you're doing it based on this prior realizations.
So this is sequential.
So the right hand side would be sequential, the left hand side would be joint.
Okay. So it'll be like we are saying it'll be same. We do it sequentially or jointly.
Exactly, but sequentially as in you don't compress them independently of one another. Right. So you compress this. It's not easy to design this particular compressor, but the optimal compressor would do that. So the optimal sequential compressor would achieve this particular rate. The optimal joint compressor would achieve this particular rate, and both of them essentially achieve the same thing.
So whether it's optimal or not, this equality will hold.
No. Well, if it's not optimal, it will achieve some rate above this. If this is not optimal, it will achieve some rate above h of x1, x2, x3, but it could be anything, right? It could be arbitrary.
So this equality is only we are considering it to be optimal.
Yes. All right. And this can be generalized to n random variables. So h of x1 through xn is h of x1 plus h of x2 given x1 plus x3 given x1 and x2 and so on. Right. So notationally, you can write this as h of x1 through xn or h of x superscript n is the summation of all I going from 1 through n of h of xi given x1 through xi minus 1. So the entropy of a sequence is equal to the sum of the entropies of all the xi's given the past, x1 through xi minus 1. If you view them as random variables occurring one after the other, x1 through xn, then the entropy can be, in the chain rule says that the joint entropy is equal to the sum of the uh, the conditional entropies of xi given all of the past x1, x2 up to xi minus 1. Okay. We can also write a similar chain rule for mutual information. So now assume that you have a particular system, let's say a channel, where you give which has one input x and two outputs y and z. Okay. So what is the amount of information that you're getting about x given both y and z? So it turns out to be the mutual information between x and y comma z, and it is given by the following quantity. So it is summation over all x, y, z, p x, y, z log p of x, y, z given p of x, y times p of z. Okay, or another way to write this, perhaps, which looks better, x, y, z of x, y, z log p of, oh sorry, there's a mistake here, so this should be p of x times p of yz. P of x times p of yz, because of the mutual information between x and y comma z. Okay, so one way to write this is, it is a summation over all x, y, z, p of x, y, z log p of x given yz divided by p of x. Okay, because p of x, y, z divided by p of yz is p of x given yz. All right. Now, once again, I can sort of split this into two in the following way. So I'll start with the first expression, summation over all x, y, z p x, y, z x, y, z log. I want to somehow split this into a mutual information between x and y and a mutual information between something else. Okay, so I'll keep this as p xy of xy times p of z given xy. And I'll do something similar in the denominator as well. So it is p of x times p of y times p of z given y. Okay, so this is a summation over all x, y, z p of x, y, z log of p of xy by p of x, p of y plus, so I'll split this log into two. So one containing this term and the other containing the remaining terms. Okay, plus log of pz given xy by p of z given y. Okay, All right, so this is summation over all x, y, z, p of x, y, z, log p of x, y by p of x, p of y, plus summation over all x, y, z, p of x, y, z times log of pz given xy by pz given y. Okay, so the first term, now these terms don't depend on z, right? So effectively I can marginalize out z from this particular expression. So it is summation over all yz log p of xy by p of x, p of y, summation over all z, p of x, y, z. So I can marginalize out z. Plus summation over all x, y, z, p of x, y, z, log p of z given xy by p of z given y. Now let's say that I want to multiply and divide this term within the log with p of x given y. Okay, I've just multiplied and divided by p of x given y. Now what happens to the first term here? Sum over yz. I marginalize with respect to z, so I just get p of xy log p of xy by p of x, p of y, plus, what about the second term? It is a summation over all xyz, pxyz log p of, so it's p of x given y times p of z given xy. So it is p of x comma z given y by p of x given y times p of z given y. Right, so far I've done nothing fancy. I have just sort of just split the term. So I had a joint distribution and I split it into two terms, right? And I'm just simplifying it, nothing more.
Second, explain the last two steps, sir. Second last step.
This one?
Yes, sir. How did we get two summations? Once we marginalize.
So which one? So how did we get this?
Yes, sir.
Well, I had just this, right? I had summation over all p x y z log p of x y by p of x p of y, right? And I'm summing over x, y, and z. Correct?
Yes, sir.
So it is basically three summations: summation over x, summation over y, summation over z.
But sir, like the step says yz, summing over yz, and then summing over y again, sir.
Oh, sorry, this is z.
Okay. Right. But how do we miss out x? We are not summing over x, or we are keeping x.
Okay. Sorry, that's a typo. So this should be just xy. Thanks for correcting this. So it's summation over all xy and summation over all z. Right. Sorry about that. Is it fine now?
Yes, sir.
Okay. Thanks. Okay. So now what is the first quantity equal to? What is this?
So the KL divergent.
Something more familiar? This is just IXY, right? So it's summation P of xy log P of xy by P of x P of y, which is just the mutual information between x and y. The second term is what we call the mutual information between x and z given y. Okay. So the amount of mutual information between x and yz, x and yz is equal to the mutual information between x and y plus the mutual information between x and z given y. Now there's another way to sort of get this. So we derived a chain rule for entropy, and we can use this to derive a chain rule for the mutual information. So I can write this as h of yz minus h of yz given x. This is just the definition of the mutual information. Now we can apply the chain rule of entropy for both of these terms. So this is h of yz is h of y plus h of y given z minus I have h of yz given x, which I can write as h of y given x plus h of z given x and y, which is h of y minus h of y given x. I've just brought this term to the left plus h of y given z minus h of z given, I'm sorry, there's a mess up here. So this should have been h of z given y So h of yz is h of y plus h of z given y. H of yz given x is h of y given x plus h of z given x and y. Now just rearranging, I get that this is equal to h of y minus h of y given x plus h of z given y minus h of z given x and y. Now this quantity, h of y minus h of y given x, is the mutual information ixy plus this quantity, h of z given y minus h of z given xy, is the mutual information between x and z given y.
Sir,
Yes.
1 minute. So this, can you explain again, sir? Like the first line, the mutual information between X and YZ, you've taken like that. So the second line, so H of YZ is H of Y plus H of
Z given Y. For this, I've used the chain rule of entropy, which we just proved over here.
okay.
All right. So this is chain rule of entropy. Okay. So the condition, so remember that, so in general, I of, say, some quantity, I of X, Y given Z, no matter how many variables there are. So let's suppose that you have I of, say, X, Y, UV given something else, I'm not sure, W. So if you have any sort of conditional mutual information of this form, this is always going to be equal to, in terms of the entropies, this is H of the first, any one of these conditioned on W, X, Y given W, minus the same entropy, the same quantity that you had over here, X, Y, conditioned on all of these things, U, V, and W. U, V, and W. Right? So similarly, if I wanted to write it in terms of U, V, then you write this as H of U, V given W, W minus H of U, V given everything else, so X, Y, and W. X, Y, and W. So the amount of information between two quantities, given that you already know some other quantity, is the amount of randomness of one, given what you already have, minus the amount of randomness that is remaining in this, given that you observe everything else. All right, so that is H of UV given W minus H of UV given X, Y, and W. Okay, and in general, the chain rule of entropy says that if you have any H of A, B given C, then you can write it as H of A given C plus H of B given AC. Right, so it's H of A, the first one, given C, plus the H of the other one given A and C. Whereas the mutual information, the first argument is the same in these two terms. Okay, that's just to sort of help you remember. Okay, so you can generalize this to arbitrary number of random variables.
Sir, is there no input output differentiation in the XY and then ABC and those things?
It's symmetric, right? So the amount of information, so it doesn't matter whether XY is the input and UV is the output, or UV is the input and XY is the output. The amount of information that you get about one, about the other, is the same as you get about the second one given the first one.
Right, sir.
Okay, and you can generalize this similarly for any number of y's. So the mutual information between x and y1 through yn, given some other random variable w, is the summation over all I going from 1 through n of I of x yi, given y1 through yi minus 1 and w. So it is I of x y1 given w plus I of x y2 given y1 and w plus I of x y3 given y1 y2 w and so on. Okay, any questions? Okay, so now we've seen these chain rules of mutual information, which are helpful if we have a number of random variables. We don't have just one random variable, but we have a sequence of random variables. So in particular, what is maybe important to note is that if the random variables are independent, right? So if x and y, sorry, if let's say x1, x2, x3 are all independent, xn are IID random variables, or even if they are just independent but not necessarily identically distributed, then h of xi given x1 through xi minus 1 is equal to h of xi given x1 through xi minus 1. Remember that pxi given x1 through xi minus 1 is equal to pxi. So this is equal to h of xi, therefore h of xn is equal to h of x1 plus h of x2, so on up to h of xn. Right? But in general, if the xi's are not independent, then you cannot say that the total amount of uncertainty of x1 through xn is equal to the sum of the uncertainties of x1, x2, and xn. So the joint entropy is equal to the sum of the individual entropies only if all of the xi's are independent. All right? Okay. So now that we've seen some properties of entropy and mutual information, we also want to know if these are convex functions, if these are non-negative functions, and so on. All right, so let's recall the definition of a convex set. So if I give you an arbitrary subset of Rn, when do you say that this is convex? So when do you say that a set is convex?
Sir, for any 2 points belonging to the set, the entire line segment joining them should be lying inside the set.
Correct. So you take any line, take any 2 points, let's say x and y, and the line segment joining between these 2 points should also be within the set. Right. So if you take any alpha in 0 to 1, then alpha x plus 1 minus alpha times y is a parametric representation of the line segment between x and y. X, take any 2 points in the set, then the line segment should also be within the set, right? So in this example, at least the way I've drawn, this is a convex set, whereas this is not convex. If I take this point and this one, then the line joining these 2 points is not within the set. So therefore, this is not a convex set, not convex, whereas this is convex. So if you take any polygon, it is, any quadrilateral, it is convex. Any triangle is convex. But then you can potentially construct sets which are not convex. Right? So this is a convex quadrilateral. This is a quadrilateral which is not convex. Every square is convex. Right? So what is a convex function? So if you have, let's look at real valued functions. So you say that this is convex if it looks like sort of it has this bowl shape. Right? So in a similar way, just like we define convex sets using line segments, we say that the function is convex if you take any 2 points on this curve and draw the line segment between these 2 points, then the line segments must always be above the curve. Right? So that is when you say that the function is convex. So this function is not convex. Over here it is convex, because no matter how I draw a line between 2 points, it is always above the curve. Whereas if I take, let's say, this point and this one, then there is a point which is above the curve, and this line segment is also below the curve. So this is not convex, whereas this is convex. So no matter how I draw a line between 2 points, the line is always above the curve. Right? Or f of alpha x plus 1 minus alpha y, which is on the curve, is always below the line segment alpha f of x plus 1 minus alpha f of y. Okay, so this is the definition of a convex function. And it's said to be strictly convex if this inequality is strict. So the line segment is always above the line segment is always above the curve, strictly above the curve. Okay, so for example, a function of this form, right? So this function over here, this is convex. So maybe let me draw it a little better. So this function, is this going to be convex? Okay, so as a homework, just check whether this function that I've drawn over here is convex. Also think about a function which is not strictly convex. Yes.
It's not convex, sir.
It is not convex because I can draw the line segment between these 2 points and the curve is above the line segment. So it is not convex. So you can check for convexity using the second derivative. This is that you should have seen this in a previous, in your basic calculus course. So if the second derivative is greater than or equal to 0, then the function is convex. All right. And if it's strictly greater than 0, then it is strictly convex. Okay, so that's another way of parameterizing convexity. So as a homework, just check whether these three functions are convex: log x, x squared, and x log x. Okay, are these convex? Okay, so we'll stop at this point. If there are any questions, then I can take them.
So for the convex set that you defined, so like it has some tetrahedral shape and those things. Is it like geometrical interpretation that you gave, or it, like in case of a set form? So how do we
So this is the formal definition of a convex set, right? For every 2 points within the set, if the line joining the two, so if alpha x plus 1 minus alpha y is also in the set for every alpha between 0 and 1, then it is a convex set. So this is a set theoretic definition. But what is the geometric interpretation? The geometric interpretation is that given any 2 points, the line joining these 2 points is also within the set, right? So if you draw this, if it is possible to draw it, and then if you draw any line between 2 points within the set, then the line should also be within that particular region. Otherwise, it is not convex.
And the interval is supposed to be closed interval, so like 0 and 1, you're considering?
Yeah, it's a closed interval. So obviously, you know that if alpha is 0 or alpha is 1, alpha equal to 0, then what is alpha x plus 1 minus alpha y?
Y.
It is y. And you know that y is anyway in the set. Similarly, if alpha equal to 1, what is alpha x plus 1 minus alpha y?
X.
It is x. And you know that x and y are anyway in the set, right?
Yes, I got it.
So that's an assumption. Any other questions?
So will you be sharing these notes in the website?
Yes, I'll upload these today.
Okay, sir. Thank you.
Sir, about the exam.
Yes.
Sir, can we expect the questions to be like in the assignments?
Yeah, it will be something similar. And most of them will cover topics that we did in the last 2 weeks or so.
Okay. So it will be from Thursday evening to Friday class timing, right?
Yeah, roughly. So Thursday evening to sometime on Friday. I'll maybe specify the exact time.
Okay, thank you.
Sir, you conducted 3 quizzes, sir.
Correct.
I have not registered earlier, sir. Later on, only I joined the course. So I
Okay.
missed the very first quiz that you conducted.
So you sent me an email previously?
No, sir, I didn't send an email regarding this thing, sir.
Okay, fine. I'll check. Sure. So for people who registered late, I can give a makeup quiz.
Yes.
So in similar lines, actually, I missed quiz 2 because I had a prior one. I didn't know that at that time. Is there a possibility I can get a quiz 2 makeup in any way? So
I generally assume that you informed me in advance.
I completely understand. It's just that's the reason I didn't ask, because it was my mistake. That's the reason I was hesitant to ask this earlier.
Because I think I had announced in advance that there will be quizzes in class, right?
Yes, so like that's the reason I was a bit hesitant to ask this. The last one I'm asking if it's
I'll think about it.
Okay, sir. Thank you.